So we'll be live in a minute. Okay, again, we're going to move pretty fast today. It's all review, although it has been quite a while since we've seen this stuff. So I'm going to jump as fast as I can through the content, and then we'll get into a couple questions where you can help me out. We left off with limits. So I'm going to go through curve sketching, related rates with derivatives and integrals, and then leave you with the homework. So to get from limits to derivatives, we use the formal definition of a derivative. So this is every derivative is really a slope. If we take the limit as our change in x approaches 0, hello Eileen, then we'll have a derivative at, we'll have a slope at 1 point instead of a slope between 2 points. So if this is x f of x and this is x plus a little bit, then f of x plus a little bit. So I've got some change in x between them. And we take the limit as that change in x approaches 0, we'll have a slope at 1 point instead of 2 as this point comes closer and closer to the other. They eventually touch, and we get a slope at 1 point instead of 2. So last time we were able to solve these using the formal definition of a derivative. This time though, we've got a shortcut with L'Hospital's rule. So as long as we plug in h equals 0 and we end up with 0 over 0 or infinity over infinity, we can use L'Hospital's rule and cheat. So I'm going to start with Aileen. If I plug in h equals 0 right now, I'll have the sign at 5 pi 6. What's the sign at 5 pi 6? Okay, is there any chance you can turn up your microphone for me? 1 half, there we go. So this is 1 half minus 1 half, or 0. Oh. 0 over 0. Which means we can use L'Hospital's rule. L'Hospital's rule says if I get 0 over 0 or infinity over infinity or negative infinity over infinity, then we can derive the numerator and denominator separately and take the limit again, and that will be the same thing as the limit of the original function. Okay, so I'm going to derive the top and derive the bottom separate. Aileen, still with you? What happens when I derive the top? Okay, cosine at 5 pi 6 plus h. So I would multiply by the derivative of the inside function, but the derivative of the inside function would be 1. Okay, and then over 1 on bottom. We're going to take the limit as h approaches 0. So what's the cosine at 5 pi 6? Perfect. So that's what this whole limit should be equal to then. Okay, Kelly for the next one. If I plug in 0, what's the cosine at pi over 6? Root 3 over 2. So this is root 3 over 2 minus root 3 over 2 is 0 over 0 again, which means we can use L'Hospital's rule. So what happens if I derive the numerator?
Negative sign of root of pi over 6 plus h.
Over 1. So we're deriving the numerator and denominator separately. We're not using quotient rule. We're using L'Hospital's rule. Okay. If I plug in h is 0, I get the sign at pi 6 here times negative 1. What's the sign at pi 6? 1/2 times the negative 1 is negative 1/2, should be my answer. Okay, over to Sarah next. Sarah, first I'm going to plug in 0 for this, so I have negative 1/3 raised to the 5th power. 3 to the 5th power is 3, 9, 27, 81, 243. So this is really, because we're an odd power, negative 1 over 243 plus 1 over 243 over 0 is 0 over 0. So that tells us we can use L'Hospital's rule, which means if we derive the numerator and the denominator separately, and then plug in our value again, we should be able to get the answer for the limit. Okay, so Sarah, over to you. What happens when you derive the top? Okay, negative 1/3 plus h to the 4th power, and then I would multiply by the derivative of the inside, which is 1. Okay, over, when I derive the bottom? 1. Okay, so I'm going to take that, and I'm going to plug in our limits. So this is the limit as h approaches 0. So if I plug in 0 here, I'll have negative 1/3 raised to the 4th power. That's 1 over 81. So my final answer would be 5 over 81. Okay, I'm going to leave myself a little bit of space. Aileen, back to you. If I plug in 0, I get 0 over 0 again, so we can use L'Hospital's rule. What happens when I derive the square root of 4 plus h?
One half times 4 to negative 1 power.
1/2 times 4 plus h to, say again, what power?
Negative 1/2.
Negative 1/2, perfect. Over 1 when I derive the bottom separately. Okay, so this is, if I have something raised to a negative exponent, you can move it to the bottom of a fraction. So I'm going to do that. This will become 1 over 2 times 4 plus h raised to the positive 1/2 power. And if I'm raising something to the 1/2 power, that's a square root. So this is 1 over 2 square root 4 plus h. Okay, then I'm going to plug in h is 0. And what should I get for my answer?
1/4.
1/4, perfect. Square root of 4 is 2 times 2 is 4, both on the bottom of that fraction, gives me 1/4. Okay, let's check really quick. And we're good. Okay. Last part of this before we go to related rates is a quick review of curve sketching. So what I've got here is a table showing our first derivative. So this is slope. And our second derivative, or concavity. So for example, if our original function was a function of height in terms of time, then our first derivative would be velocity. How fast is the object rising or falling? If that velocity is negative, then the object is falling. If that velocity is positive, the object is rising. The second derivative would be acceleration. So my concavity in this case represents acceleration. My slope represents velocity. And my original function represents height, which is vertical displacement. So, if we did something like this, so I'm going to drop a ball into the water. That ball is going to go underwater and then float back up. So you wouldn't be able to see it there, would you? And then pop out of the water again. Okay. As that ball is falling, so that's from point A until point C. The ball's height is decreasing, which means my vertical velocity is negative. So this would be true. From A to C, our height is decreasing. But how it is decreasing is different from A to B than it is from B to C because my concavity is different, our acceleration is different. From A to B, my acceleration is due to gravity. My net acceleration is going down. So you can see our slopes, which would represent, change color here. Our slopes, which would represent how fast this ball is falling, are getting more and more negative as we go. In this case, I am decreasing because our velocity, our slope is negative, and concave down because our acceleration is also negative. So my shape of my curve looks like this. Decreasing, concave down. Velocity is negative, acceleration is negative, just like we're falling before we hit the water. After we hit the water, we have a buoyant force that pushes up, and it's stronger than the force of gravity, so our net acceleration actually goes up. Even though the ball is still falling from B to C, it's still going down, so my velocity is still negative. My acceleration, the force pushing up against me, is positive. So you can see even though our velocity is negative, our slope is negative, we're getting closer and closer to zero as we go. I am decreasing for our height, but our height function is concave up. Decreasing, concave up. After point C, we start increasing. So I guess I should label these. This is from A to B, B to C. Okay, so from C to D, I am increasing and my acceleration is also pushing the ball up. So the height is increasing and our acceleration is also causing our increasing rate to go faster. It means velocity is positive and acceleration is positive. First and second derivative are both positive. And you can see our slopes are getting more and more positive as we go. That's from C to D. And then if we get fast enough that the ball actually leaves the surface of the water, then suddenly we don't have any buoyant force acting on the ball and it's just gravity. And so our acceleration will be negative again. But the ball is going up now. So in this case, my vertical velocity is positive because the ball is still going up, but our acceleration is negative because gravity is pulling it down. So even though our slope, our velocity, is positive, it's getting closer and closer to zero as we go. From D to E. Okay, any questions on slope or concavity? Okay. So really quick vocabulary then. Whenever our first derivative, that's our slope, is 0 or undefined, we have a critical point. Whenever our second derivative is 0 or undefined and the concavity changes from positive to negative, we have a point of inflection. So Aileen, can you name a couple critical points for me that are showing on this graph? Okay, b is 1. Um, sorry, I'm still having a hard time hearing. You say one more time?
K.
K is not a critical point, no. Critical point is whenever the slope, that's our first derivative, is 0.
F
Okay, f is good.
and J.
J is good as well. Okay, I've got 2 more.
D and H.
D and H, perfect. Okay, B, D, F, H, J are all critical points. Kelly, what are my points of inflection?
B.
Say one more time, I'm sorry.
B.
B is a critical point because our slope is 0. Point of inflection is when the second derivative, so that's the acceleration, or the concavity is 0. For me, it's easier to see when the concavity changes. So for example, my concavity at point B changes from being concave down to concave up on this graph. Okay, so for this graph, what are my points of inflection?
C. E. G and I.
Perfect. C, E, G, I. Okay. A relative extrema is a point that is higher or lower than the points around it. So they could be either relative minimums or relative maximums. So these are subcategories. A relative minimum is a point that's lower than the points around it. A relative maximum is a point that's higher than the points around it. So if I was a relative minimum, my first derivative would be 0. That means my slope is 0. And my second derivative would be positive. So I would be concave up with a slope of 0. Sarah, can you give me one point that is a relative minimum? A is not a relative minimum, no. There aren't any points to the left, so we don't have any points around it. Okay, D is good. I've got one more showing. H, perfect. And then, Aileen, can you give me relative maximums?
E. F. J.
B, F, and J, perfect. Okay, then an absolute minimum is the lowest point on the interval. Now, these do not have to have a slope of 0 or points around them. It just has to be the lowest y value anywhere. Now, the lowest y value, if it doesn't have a slope of 0, so if it's not a relative minimum, then it would need to be a critical point, which means the slope is undefined or an endpoint, start point, end point. Aileen, what's our absolute minimum value on this graph?
A.
Point A, perfect. Kelly, what's the absolute maximum value on this graph?
J.
J, perfect. Okay, any questions on vocabulary? No. Okay, so I think we talked earlier about this, but one way that this could be used outside of physics, Walmart actually uses this to track their sales for a fashion. So let's say this is sales per day. And we've got a graph that looks like this. So typically you've got a fashion that looks something like a bell curve. People really want to buy it when it's hot, and then kind of the trend will end up dying down over time. So let's say, as an example, Pokemon released in 1998. There were Pokemon cards that people would buy that were really popular for about a year or two, and then nobody wanted to buy them anymore. So initially, more and more people were trying to buy these cards as people found out that they existed and were popular with other people. Eventually, our sales hit a high point. And then our sales started decreasing. What Walmart will do, that no other company was doing at the time, was instead of buying more Pokemon cards to put in their stores until sales started to decrease. So that would be until the maximum point when sales changed from positive to negative per day. Walmart would instead look at the second derivative, so they would look for their points of inflection. When does the concavity, the acceleration of sales per day, actually change? At this point, the point of inflection, Walmart would stop buying new Pokemon cards. And the reason why is because all of the Pokemon cards that they had already bought and were in their store would be able to be sold in all of their Walmarts before the trend actually died. And that meant they didn't waste any money buying cards that they couldn't sell, or more importantly, waste shelf space, putting up a bunch of Pokemon cards that wouldn't sell in the future. It ended up being so effective that in my hometown, no other stores could compete. So Walmart was the only retail store in my hometown for almost 10 years. Okay, changing gears and looking at some related rates. I'm going to do a derivative example, and I'm going to have you guys help me out with an integral example. So I've got our camera that is looking at this space shuttle as it launches. The space shuttle is launching according to a position equation. Oh, just realized I'm at the 30-minute mark. I might just flash for this and explain then. Okay, our space shuttle's position equation is s equals 50t, where s is measured in feet and t is measured in seconds. The camera is 2,000 meters away from the launch pad. I want to find the rate of change in the angle of elevation of the camera. How fast does this angle change? 10 seconds after launch. So what I'm really looking for is the change in our angle over time. How fast does the angle change? Which would be in radians per second. So I'm going to start out with relating what I know to what I don't know. I need a relationship between our angle and s and 2000, which are the two parts that I do know. Since after 10 seconds, we know how much s will be. And then because I'm actually looking for d theta over dt, I'll need to derive that relationship. So I have an angle, an opposite side, and an adjacent side, so I could use a tangent relationship. Tangent is opposite over adjacent. And derive that to figure out what's happening over time. So if I derive this left side, derivative of tangent is secant squared. And then with chain rule, I'll have to multiply by d theta over dt, which is what we want to solve for. 50 over 2000 is 1 over 40 times t. If I derive that, I'll get 1 over 40, just the constant in front. Because secant squared is the same thing as 1 over cosine squared, I can multiply both sides by cosine squared and get d theta over dt, which is what we're looking for. Okay, so that gives me cosine squared over 40 is d theta over dt. Then we can plug in at t equals 10 and see what happens. So at t equals 10, our space shuttle has risen by 500 meters. This would be 500 over 200 is 5 over 2. I can take the arctangent of both sides to get the angle, which you could either plug in a calculator or just leave as arctangent 5 over 2 and set up your triangle relationship. So this is opposite is 5, adjacent is 2, solve for c. So I could say c squared equals 25 plus 4, or c equals the square root of 29. And then when I go to take the cosine of that, I'll have d theta over dt, I'm going from this line, d theta over dt is 1 over 40 times the cosine at that angle. So the angle that gives us a tangent of 5 over 2's cosine would be adjacent over hypotenuse is 2 over root 29. Clean this up just a little bit. C, which we solved for as square root 29. So I've got times the cosine was adjacent over hypotenuse, and I'm going to square it. Gives me 4, and the 40 can cancel to be 1 over 10 times 29 squared. Okay, is how I would solve this if I had to do it by hand. Or we can type it in a calculator and we can get a decimal answer in radians per second. Any questions on what we did here? Okay. So then I'm going to hand it over to you guys and do some related rates with integrals instead. Starting with, I can't remember who I was on last time. So I'm going to start with Sarah. What I have here is a rate at which people are entering the line for an escalator. An escalator is a set of automated stairs. So I've got a rate at which people are entering the line for the escalator. Is RT, measured in people per second. So it's already a velocity. Okay, we were also given that people are exiting at a constant rate. So they're getting off the escalator at a rate of what I'm going to call LT. How fast people are leaving is 0.7 people per second. Call this velocity in and velocity out. Okay, what I want to know is how many people entered the line for the escalator from 0 to 300. So I'm over to Sarah. If I have here RT, a velocity of how fast people are entering the line in people per second, do I need to derive that or integrate to figure out how many people entered the escalator? Integrate, perfect. Anytime I'm integrating, we're multiplying our units together. So this would be people per second times seconds gives me people. Anytime you're deriving, you'll divide your units. So if I derive this, you'll get people per second divided by seconds, which would be people per second squared, or acceleration. Okay. So we want to integrate, which means we're multiplying our units together. So that I've got our people per second is RT times how much seconds have passed, dt, the change in time. Okay, from second number 0 to second number 300 should give me the total people who entered the line. Okay, now this is a with calculator question that I pulled from an AP exam. So I'm going to do this in a calculator. The first thing I'm going to do, since I'm going to have to reuse this rate it looks like for several of these problems, is I'm going to hit y equals and then type in our rates. This is 44 times x over 100 cubed times 1 minus x over 300 to the 7th power is how fast people are entering the escalator. And then just in case we need it, we've got a constant rate people are leaving later of 0.7. So right now y1 is RT and y2 is LT. Okay, then I'm going to quit. And we're going to integrate. So that's math, and then the 9th option down is integration. I'm going to integrate our function for y1, which is in the calculator. So that's variables, y variables, function y1. I'm going to integrate in terms of x from x equals 0 to x equals 300, and we'll get our answer. So we have a total of 270 people that entered the escalator. Again, because we integrated, we multiplied our units together. So RT was people per second, and we just multiplied by dt, which is your change in seconds. So our seconds will cancel, and we'll be left with people for our units. Okay. Part B. During the interval from 0 to 300, there are always people in line for the escalator. I want to know how many people are in line total at the time t equals 300. Okay, I didn't highlight this last time because we didn't need it last time, but there were already 20 people in line at t equals 0. Okay, so Aileen, if I want to know the total number of people in line, and we've got some people entering, some people already on the escalator, and some people who have already left the escalator. How can I set up a general equation for how many people are still in line for the escalator?
N plus
Okay, so people in line, I've got 20 people that started in line, plus what?
plus the integral 0 to 300.
Okay, you're adding here, so do I need to use the people who are entering the line or the people who are exiting the line?
Entering
Entering? Okay, so that, what should I write?
0.7.
0.7 is how fast they're exiting.
Then x minus 0.7.
I'm not sure what x would be in that case, but we've actually got another function, not 0.7, that's measuring how many people per second are entering the escalator. People are entering. I just realized this is actually cut off for you guys, isn't it? You can't see the top line, can you? Top line says people are entering the line for an escalator at a rate modeled by the function r, which is given here. So this is RT is measured in people per second, is the rate people enter the line. Okay, so this should be RT in terms of time. I've got some people that were already in line. Let's do this in better English. This is people already in line plus people entering the line minus what?
Exiting.
People exiting the line. Okay, how can I get the total number of people that exited? So minus what?
0.7.
I'm going to have to use 0.7 somehow, but 0.7 is a rate. That's people per second, not people.
DT.
0.7 times dt. Okay, if I'm multiplying, that means I do need to figure out what I'm multiplying, so I'll need to integrate as dt changes from what to what. 0 to 300 again. Perfect. Okay, and that should give us the total number of people in line. So I'll do that really quick. We have 20 people already in line, and then I'm going to add math 9. The integral of how many people per second are entering the line in terms of time, which will give me the total number of people that enter the line from time 0 to time 300. So that's variables, y variables function y1 for us in terms of x from 0 to 300. I guess I didn't need to do that because I already did that once up here. I could have just typed 270, but well, 20 plus 270 minus, I'm going to integrate our rate people are leaving, so that's people per second that are leaving the escalator times the number of seconds they've left would be the integral of 0.7 people per second in terms of time from 0 to 300. Math 9, which we could have shortcutted and just multiplied 0.7 times 300 because that's a constant rate, but I'm going to do this anyways. As variables, y variables function y2, which is 0.7 in terms of x from 0 to 300. So again, what we just did, people who are already in line plus people total who entered the line in the 300 second window minus people who left the line in the 300 second window gives us a total of 80 people in line at the time 300. So 300 seconds after we start, we still have 80 people in line. Any questions on what we did here? Okay, here it is again. Part C. After time 300, you'll notice this is a piecewise function, and our function actually changes. So after 300 seconds, no one is entering the line. So now, after time 300, we've got some people still on the escalator, and a rate, LT, equals 0.7 people per second, at which people are leaving the escalator. Kelly, I want to know when the first time would be that there are no people in line for the escalator. So first, what's my equation for people in line after 300? Okay, I'm going to set this equal to 0 for my next step. This is people in line after 300 would be okay. Before 300, it was people in line are people already in line plus people entering minus people exiting. After 300, no one is entering. So what should my general form be?
20 minus people leaving.
We're that would mean I'm adding people who are leaving, but we're close. This would be the total people in line at t equals 300. And then no one is entering the elevator, they're just leaving. So I'd have to subtract the people leaving. Okay, for part B, we found how many people were in line at 300 was 80. So I've got 0 equals 80 minus the total number of people leaving. What's the total number of people leaving? If they're leaving at a rate of 0.7 people per second.
Uh, 80.
80 is the total number of people in line right now. Right now we've got a rate. LT is 0.7 people per second. How can I get from that rate, that velocity, to a total amount?
Integrate 0.7 dt.
Perfect. I'm going to integrate 0.7 dt. However, RT is actually a different time because now I'm measuring time after 300.
Oh.
So I'll have to go back and fix that after we solve this. But this is 0 seconds after 300 to t seconds after 300. And I want to know, I want to solve this equation for t. Okay, so if I integrate 0.7 dt from 0 to t, what will I get? If I integrate 0.7 dt, what should I get? 0.7 t. Okay, then I would plug in t and then subtract what happens when I plug in 0. So that's just going to be 0.7 t. So that gives us an equation. I am out of space, so I'm going to go ahead and draw up here maybe. So I've got 0 equals 80 minus 0.7 t. And I need to solve for t. So I'll move this over. 0.7 t equals 80, or 7t equals 800. Multiplied both sides by 10. T is 800 over 7 seconds. However, that t is time after 300. So I'm going to have to add 300 to that to figure out what lowercase t this would be. So t equals 300 plus capital T equals 300 plus 800 sevenths seconds. Okay, so the first time that there are no people in the escalator would be 800 divided by 7 plus 300 is time number 414.3 seconds after we started. Here it is again. So we knew the number of people in line at 300 was 80. Since we've got 80 people and we're leaving at 0.7 people per second, if I divide 80 people divided by 0.7 people per second, when I divide by a fraction for this unit, I can flip and multiply. So this would be 80 people times 1 over 0.7. I'd flipped that and multiplied. So this is now seconds per people because we flipped it. My people will cancel and I'll be left with seconds. 300 plus 80 over 0.7 seconds is 414.286. Slightly different method, but gets the same result. Any questions on this one? Okay. Last one, part D. I want to know at what time the total number of people in line would be at a minimum to the nearest whole number. Okay, Sarah, from our curve sketching part that we just finished, how do I know when people in line would be at a minimum? So how do I know when a function is at a minimum? I'll ask another way. If our function is at a minimum, what does the slope have to be equal to? 0, perfect. Okay, so I want, if I want the people in line to be at a minimum, then I will need the people per second to be 0. Or if it's an absolute minimum, so if the slope is 0, that would give us any relative minimums or maximums. If I'm looking for an absolute minimum, that could be a start point or an end point as well. So we could test both. Okay, so I'm going to take our rate, which is RT. Change in people in line is equal to our rate in minus our rate out is our total change. And I want this to be equal to 0. RT minus LT. Now, I don't want to solve this by hand because this is a crazy function. But if you notice, this can only be true if RT is equal to LT. So I'm going to use that to solve. So in our calculator, I've got y1 right now is RT, y2 right now is LT. So I'm just going to calculate the intersect. So I'm going to give myself a window. I need to be able to see the first 300 seconds. And calculate the intersect. So there's our RT and our LT. Okay, that's a little bit small. So I'm going to go ahead and hit, I could just change the window counting these, 1, 2, 3. So my highest point's a little bit between 4, and my lowest point is somewhere around negative 1-ish. I'm going to do that. So 4 and negative 1. We should be able to see our graph now. Okay, so I need those two intersects, intersect A and intersect B. So I'm going to second calculate an intersect. It's going to ask me for a first curve, second curve, and a guess. So here's my first curve, second curve, and my guess is when they cross. I'm going to leave it there, and it'll give me B. So B is 166.6 seconds. Second quit. X store as B in case we need it. Okay, and then I need A as well. Second calculate an intersect. So here's my first curve, second curve, and my guess needs to be closer to the left side now. So I'm just going to drag this over until we're closer to the left. and hit enter. And it should give us our intersect A, 33.01. Again, second quit X store alpha A in case we need it later. So now I've got A and B stored in the calculator, so we don't have to round if we need to use them ever. Okay. So I'm going to take a look at my graph again, so I can probably just answer this graphically, actually. I'm going to Aileen next. Aileen, taking a look at our graph, where this flat line is the rate at which people are leaving, and the curved line is the rate at which people are entering. Would intersect A be the minimum, or would intersect B be the minimum of people on the elevator?
B.
Okay, I'm going to draw out really quick. So we had a graph that looked like this, where I'm going to use different colors. This is RT was kind of like a bell curve shape, and LT was a flat line. Okay, so I'm just going to take a look at what the first derivative test would look like, maybe, and perhaps this will be easier. So for my first derivative test at our two critical points A and B, looking at our change in people, so that's P prime T. For this first part, RT is less than LT, so should my people in line be positive or negative?
Negative.
Negative. Okay, change in people is negative. Okay, then between A and B, would the people in line per second be positive or negative?
Positive.
Positive. Okay, and then after B?
Negative.
Negative. Okay, so taking a look at our slope changed from decreasing to increasing at A, and from increasing to decreasing at B. Which one do you think is the minimum?
A.
A. Okay, so I'll draw it out again. Our slope changed from negative to positive, so this is a minimum. And our slope changed from positive to negative at B, so this is a maximum. I can't really see that minimum, so I'm going to rewrite. Ah. There we go. Okay, so my minimum is at A. Now, because we were decreasing up until that point, actually shouldn't. Well, I guess I do need to test the endpoint. Okay, at the endpoint. Well, no, we can just look at areas. Okay, what I'm debating doing here, just to explain what I'm talking about, is we know we had a minimum, so I know that the start point, because we started decreasing, cannot be the smallest amount of people that are in line. So it's not the start point. I know B is a maximum, so it's not B. So that leaves just it could be A, or it could be the endpoint. The way that you would tell is by using integration. So we could integrate this function and figure out how many people total were in line at A or at the endpoint, which we actually already have a formula for. Our total number of, where was it? Here. Total number of people in line at any time would be 20 plus 0 to t of RT minus 0 to t of 0.7 dt. So I guess I'll do this analytically, and we'll go ahead and calculate A. We already calculated the endpoint. We know that there's 80 people total at 300. So we'll calculate A. So for A, I'm going to do 20 plus math 9. I'm going to integrate our number of people who were entering per second in terms of seconds from 0 until A. Then I'm going to subtract the number of people who are leaving, which is going to be the integral of the people leaving per second in terms of x from 0 to A. And that should give us the total number of people who are in line for the escalator at A, which is only 3.8 people. So right now my minimum number of people total is A. At a minimum of 3 people at t equals 33.01 seconds. Okay, here it is again. So our total number of people in line is 20 plus the integral from 0 to t of the people per second who enter line minus 0.7 people per second leaving times t. We can plug in all of our t's at the start point, end point, and critical points to figure out when our people in time was at a minimum. So we started at 20. We had a relative minimum, a relative maximum, and our endpoint, which was 80 that we'd already solved for. So we already knew start point, end point. The only ones we didn't know was the minimum and maximum, and since we can't have an absolute minimum at a relative maximum, we knew it had to be the minimum or a start point or end point. Since we went down from the start point, we knew it had to be the minimum. Alternatively, you can actually plug it in and solve for all of the people using this formula and just pick the smallest value. Either way, our number of people in line at a minimum is going to happen at t equals 33 seconds when there are 4 people in line. To the nearest whole number, not round down. Okay, so then 3.8 is going to round up to 4. Any questions on anything from this? All right, so I've got 2 related rates problems for homework that are derivative based, I believe. They are easier than this one that we just did. If you've got questions, hit me up on WeChat, and I'm going to be taking those up Monday at midnight for this class. Okay, thank you guys so much for coming. Sorry to keep you a little bit over time.